let's go on. So it's my pleasure to introduce the next talk, so by Fernando Oliveira from the TU Delft. So this seems like a Dutch session. Please go ahead. So Fernando will talk about an introduction to the flag algebra theory of Rasborov. Please go ahead, Fernando.
Thank you, Monique, for the introduction. So I decided to talk about something which is not my work. So it's the Rasborov. So it's quite a famous work now.
Fernando?
Yes.
Maybe you can speak a bit louder, or?
Yes, I can try.
Yeah, now it's good.
So this is work by Rasborov. So it's from 2007. It started. So it's already some rather established theory, and it's very interesting for people in semi-definite programming. So that's why I think also people don't know it yet or don't know the details. So that's why I thought of presenting about it. So so this theory of flag algebras, it kind of, since there are no extremal graph theory people here, maybe I can say it kind of revolutionized a bit the theory of extremal graph theory. And the first problem in extremal graph theory is perhaps problem here. It's called Mantel's problem. It's from 1910, so mathematician. So it is a Dutch session. And the problem asks how many edges you can have in an n-vertex triangle-free graph. Okay, so you have a graph of n vertices and it doesn't have triangles. So how many edges can this graph have? And the answer to this question is squared over 4. So basically, you can have half of all the possible edges in the graph, because a complete graph has n squared over 2 around the edges, right? And this is the extremal example, it's called. It's a complete Biped graph. So if you just divide your vertex set into 2 parts of equal size, and you put edges between these 2 parts, then you don't have any triangles because you have a bipartite graph, so you don't have even any odd cycles, and you have n squared over 4 edges, right? And this is actually the best you can do. So that is Mantel's theorem, okay? So everything is understood in this very simple first problem of extremal graph theory, but in general, extremal graph theory asks a question like this, as I'm going to say now. So in this case, Mantel's theorem, density of a triangle-free graph is most 1 over 2. So what is extremal graph theory? So you have the concept. So you have graph F, and PF is the density of F in G as an induced subgraph. So that is just, you count how many times that F appears in G as an induced subgraph, and then you normalize by the number of subsets of size number of vertices in F. So it is the probability that if you select a set of vertices from G of the same size as F uniformly at random, that you are going to have F. So this is the density, and H is a family of you call forbidden subgraphs, right? So graphs you don't want to have, and the parameter you are interested in is this XCH, which is the maximum density in an H graph, okay? And if you want to write it in mathematics as a formula, as we are going to need it later, you want to get the supremum over every sequence of the sup of, right? And the supreme runs a sequence of graphs which is increasing. So that's the number of vertices from one graph to the next in the sequence strictly increases, okay? And you want that because if you allow for, because you want to avoid, for instance, having, for instance, a sequence which is always the same graph, like this. You could have always the same graph in your sequence, and then they are all triangle free, and the edge density is 1, right? So that's what you want to avoid. You want to avoid looking at small graphs, because small graphs can be H-free and they can have they can be complete, so they can have like edge density 1. So that's what you want to avoid. So that's why you take here the supremum. And then Mantel's theorem restated, it just says that x of the edge and triangle to 1/2, right? So that is Mantel's theorem. So you can actually notice that if you let it be the set of all finite H-free graphs up to isomorphisms, so you disregard isomorphic copies of the same graph, then you can say that a sequence of graphs is if this for every, so if when you take any graph and you look at the density of f in decay, you infinity, then this limit exists for every graph that you take. Then I call this sequence convergent. Then the first question you can ask is, are there convergent sequences of graphs that are interesting, right? Increasing sequences. And the answer is yes. So every sequence of graphs, every increasing sequence has a converging subsequence. And this is not a very amazing result. It just comes from the fact that if you look at this, which is right, you can imagine is a point in this space 0, 1, which is because the densities are between 0, 1. So this function is a point in 0, 1 to the power g, and this is a compact space by Tikhonov's theorem. So so if you have a converging subsequence, right? Because it's compact. Okay, so you can even like replace here. You can replace this by this, and you can then eliminate the limit, right? So that makes it a
Fernando?
little. Yes.
Sorry to interrupt, but
Yeah.
maybe you are sometimes moving away from the mic.
Yeah,
your
I
voice
don't know,
is
because
sometimes...
I'm just in front of my iPad.
Okay,
Here,
okay, so
so
nothing to do.
I'll
No,
try to hold
sorry.
it up a bit like this.
So like now you are far away, but
I am far away now. I'm very close, so I cannot get closer, I guess.
okay, it's okay. Then we all listen very carefully. I'm sorry.
Okay. I'm sorry. I don't know if I can change anything. So so let me know if it's too bad, and then I can try to do something. Okay, so you can change here the sequence to be an increasing sequence, and you can then eliminate the limit. Makes it a little nicer. So, all right. So I'll just quickly say, how can you try to attack this problem with the Lasserre hierarchy? And you can do the following. You can, and then you can consider the set. I called it a V here, which is a rather just because it's a space, but it's the set of all some n vertices can have. So I should have called it E. So maybe I just put it again everywhere. So I can call it E. It's the set of all possible edges that a graph on n vertices can have. And then you can just make the following very large matrix, like in Lasserre's hierarchy. You have possible edges, and so on. You have to stop somewhere, right? And then you say that is going to be zero if the union of this for the row and the column contains a graph, so contains a graph in H, right? So that is like how you would model this problem as an SDP, and then you have some constraints of some entries have to be equal if the union of the sets is the same, and you have a normalization constraints that at the empty set you have a 1 and so on. So if you model it like this, just like for the Lovász theta number, then you can model your problem as an SDP. right? For a fixed n, so for a fixed number of vertices in your graph, you can model your problem as an SDP, and then you can realize that actually for the vertices of your graph, so your vertices are numbered from 1 to n. So the labels, they are not important, right? So you can permute the labels however you like. So there is an action of the symmetric on the set n for, and therefore on this you can actually use the symmetry to reduce the size of the problem. So you can block diagonalize this. And then there are two ways you can do this. You can use a part of only, and that's what these people here did. Raymond, Singh, and Thomas did this in 2018. And then you get this algebras by Razborov. So they got again the theory of flag algebras, at least for graphs, right? Or you can actually use the full symmetry group, and it's more complicated. And then you are going to get a little different theory from the flag algebras theory. And this is a result from Tilburg. So that's an interesting thing. So you can make it, you can symmetrize it further, and then you get even smaller STPs for flag algebras. But I'm going to describe the original theory, which is another way of doing the symmetrization. And this is actually quite, because you have to understand the representation theory of a symmetric group and all this stuff. So Razborov's theory has nothing of that. All right, so coming back, so what is a limit functional? So I don't know, a functional, for now it's just a function, but it's going to be clear later why I would like to call this a functional. A limit functional for me is a function that assigns a real word, okay, up to isomorphism, but that comes a convergent sequence. So there is such that the functional f is equal to of f in GK. Okay, so we are really interested in the set capital phi. So is actually the summum where phi is functional. So that's what you want, right? So you have a limit functional on the set of all H3 graphs, and you want to maximize the where phi, and that's a very nice I mean, it's a trivial way to rewrite the problem, but it gives you a nice thing, which is it's a first step to set it up as an optimization problem. So then your question becomes, let us find a good relaxation of this. So let us find which is going to give us, but over which it is easy to optimize, so that we can get bounds for this. So I'm really, the theory of flag algebras is really about finding relaxation of. All right. So for that, I have to do a few steps. So types and flags. So I hope that everything is going to come together in the end, but we have to have some definitions before. So what is a type of something? A type is going to be an H. All graphs are going to be H3. Okay, so I always write it, but you should always keep in mind everything is H3. So H is fixed and it's in the background now. So an H3 graph which has vertex set 1 up to k. Okay, so it's a graph with labeled vertices from 1 to k. So the vertices have labels from 1 to k. So that's what a flag is. So there are, let's imagine that's the graph have the possible flags. So you have a flag, flag. You always have this flag. You have a one. You have only one, right? Which is the vertex. You have two flags. So you have and then the graph, which is one edge, and then you have several flags. Three, for instance, you have the you have right. Then you could also like permute the label. Then you get basically equivalent types, so they don't really matter, right? But you have for size 4 and 5 and 6. So this is not a type. It's just a labeled graph. And the sigma flag is a partially labeled graph. So a sigma flag is an H which has some labeled from 1 to k. And if you look at only the labeled vertices from 1 to k, you get exactly an embedding of your type there. Okay, so the type is inside. So for instance, if this is your type, so it has 1, 2, and 3, and this is the sigma flag. It's a partially labeled graph, so the labels are here 1, 2, and 3. And when you look only at the labels, okay, 1, 2, 3. It's what a flag is. A sigma flag, a flag of type sigma. If you know this, this stuff by I forgot the name of it now. The reflection positivity and all these things. Graph. This graph. I forgot. It's by Lex Schrijver and Lovas and some other people. They also have a theory where you have like these partially labeled graphs, right? So that's similar here. I really forgot the name of this theory. So. Okay, so here I have the set. So this is what a sigma flag is, and here is the set of all possible sigma flags of size n. I call it Fn. Isomorphism. And isomorphism of flags is the same as isomorphism for graphs, but now you are obliged to map the type of one flag to the type of the other flag. Okay, so if you have two flags of the same type, they are isomorphic if you can map the vertices of the one to the other and you preserve adjacency, but also you have to map the labeled vertices to the corresponding labels of the other one, right? So you have to preserve the labels in your mapping. So that's isomorphism of flags. And if you think about it, when you have then an empty flag is a graph which has no label, so it's just a graph. So the set of all empty flags is a set of all graphs of n vertices. Okay. Now you have something. You have a definition of density again. So we saw what is a density for graphs, but you can define the same for flags. And you can actually define something called a joint density, right? So say that you have a bunch of flags, F1, Ft, and P. They are sets, and then you define P of as the joint density of G. So it is, if you want to know what this is, the definition of it is as follows. Right? So you want now to find copies of F1 up to Ft inside of your sigma flag, but they have to share the type sigma. So the type sigma is, so now everybody has to be mapped inside of G in a disjoint manner. So F1, F2, and F3, they are stacked. And you want to know how many ways you have of making this mapping, right? Of finding copies of every of your flags inside of G as long as you keep the type sigma in the intersection. So in other words, it's a random experiment you want to map to the type, but you want to find these sets here. You want to find the sets U1, which is a set of size of F1 minus the size of the type. And then you want to find U2, which is this other set, it's to be disjoint, right? And you want to find U3, which is other type, so on. And you want to find them, you pick these sets at random, uniformly, they're disjoint, and you want to find what's the probability that each is. So that is your density. And the density has a very nice property, which if you have only one flag, it's very easy to see. And also for more, it's also not so hard, which is if you want to see what's the density of F, you can take a number which is between the size of F, and then you can expand. You can just run over all flags F prime, and you can try to compute F inside, and then compute F of G. Okay, and that's like conditional probability. You are trying to find, you are conditioning your event of finding a copy of F inside of G to finding a copy of F inside of G, given that you are already inside of F prime. And then if you expand this conditional probability experiment, you are going to get exactly this form, right? So you just, it's a counting argument. It's two different ways of counting the same thing. So here you are counting copies of inside of G, and here you first count copies of F inside of G inside of F prime. And you can extend this to more flags. So this is, and then you want to find one FT. Well, this is the same as you go from F1 to F, and then you try to find F and F of S plus 1 up to FT of G. So it's the same thing. It is the same thing. It is just with more flags. Okay, so you can split this anywhere you want. And the density has also something that is very nice and important later, which is a multiplicative behavior. So if you have two, then if you take this, then this are fixed. Okay, so the density of these flags it converges to the product of the densities. And you can say why this looks rather complicated, but it's not complicated. If you remember the definition of joint density, now you have only two flags, imagine, but it doesn't matter. If your graph is very large, the experiment of picking these joint sets for F1, F2, and F3 is basically the same as picking just two sets. Okay, because if you pick two sets and you don't make a point that they are disjoint, they may end up not being disjoint, right? But if your size of G is so large, the probability that they are going to intersect becomes negligible. So it goes to 0. So if you have an infinitely large graph G, the probability that you are going to pick two sets which intersect is 0. Okay, so that's why in the limit, picking two disjoint sets or picking just two sets uniformly at random is the same. So then you get this multiplicative behavior. And then finally, we can define, finally, we can try to define what's the flag algebra. Okay, so it's going to be really an algebra. So imagine that you have a convergent sequence of sigma flags. It's an increasing sequence, and it converges, which means that for every sigma flag, when you compute this it converges this limit exists for every sigma flag. Okay, so that's what it means to be a convergent sequence of sigma flags. So you have such a sequence, and you can then define the limit, or this limit phi of f to be, and then you can to be vector space over the sigma flags. So you have vectors, you have stages of sigma flags, okay, and then you can just add this thing linearly space, and when you do that, this thing becomes a linear functional of the vector space, and we call it. All right, so we call it a limit functional. That's why I called it a functional in the beginning also. The chain rule now, which I just showed, it gives you a nice property of such limit functionals. Namely, it shows that if you have a density, you can always that. So if you look at the definition, if you have a, if you compute the same as phi, right? Because this is a functional, so it goes in station. So you get phi with of f prime in AK, right? So this is basically just telling you that if you look at from the point of view of densities, the left-hand side and the right, they are the same. So you have two vectors, right? So this is an element of three vectors, and these two vectors are the same if you look at densities, okay? And we only care about density. So then the idea of Rasborov, which is like the brilliant idea of the whole thing, is like, notice, so if you're only looking at densities, and if these two things are the same, let's mod them out. Let's quotient them out, okay? So notice that this is in the, just mod it out. So let's call K sigma, let K sigma be the space which is generated. Okay, and now let's consider the coordinates of the vector space K sigma, and let's call, and this is called A sigma, and it is it's going to be algebra. Okay, it's a vector space that is immediate. Phi, if you have a limit functional, then it is also a linear functional of A sigma, because the kernel is K star K sigma. The kernel is a superset of K sigma, so it remains a linear functional. But I write B flag algebra because I didn't say what the product in this thing is yet. But the nice thing is that by making this quotient, I can define a product, and this product is going to help us later. So how do you define the product in this algebra? Well, you just define, you have two flags, okay? Let me make a map. Let me just make a product of two flags first. So if you have two flags, I define the product by using the chain rule, okay? I just take a large combined, and I say that this thing is equal to the sum, right? Sum of our H, okay? And then I want to have an element so the set K sigma. So I get a coset, okay? Quotient. Okay, so this is mapping two flags to an element sigma. Now you can this thing by linear free vector space that you can always do, right? So then you get a bilinear form, and then you can realize that this bilinear form is actually constant on constant that follows from the chain rule, and this means that you get a product on the this A sigma, you get actually you get a commutative product, right? So you get a symmetric bilinear form on A sigma. So this makes A sigma into an algebra. Okay, it's into an algebra with units actually. So the unit of this algebra, so the unit is to be the type. Okay, so the type itself is the unit. So it's an element of K sigma, or actually the whole set of the type is an element of K sigma. And if we imagine that you have here the type, so what's the probability of type? So what's the probability of getting like the type and anything else in a certain G? Well, the type is always there. It's the same as the probability of getting G itself inside of H, and this is G. Okay, so this is like just to show you that the type itself is the unit of this algebra. So let's just to make an example to fix things. Let's get an example of project. So what is the project of some flags? Okay, so here I have a type text, and here I have all. Okay, in triangle free graphs, right? So here I have a known edge, right? So I have the type, and then I have the other vertex, and I have edge, the type, and the other guy. And here I have all the flags of size 3. So I have the empty flag, one edge, right? So one edge connects the type, one connects the type, two edges with the vertex of degree 2 being the type, and two edges with the vertex of degree 1 being the type. So these are all the 3 flags that I have for this type. So what is the product of the non-edge with edge? So to compute this product, I have to expand in some size of flags, right? And the minimum size I can take is 3. Actually, what happens is that it doesn't matter the size I take as long as it's large enough. So I take the minimum size possible. So I have to compute for each flag of size 3 what is by the flag. Okay, so let's compute for each flag. So what's the joint probability of finding the empty edge, the known edge, and the edge in when I'm forced to map the full vertex to the full vertex? What's the probability of that? Well, it is 0, right? Because I never have the edge here. Okay, so this has coefficient 0 here. So what's the probability? So I have to map the full vertex here, right? So then I only have to map this guy. So if I map this guy by mistake here, I don't get I don't get a mapping. I don't get an embedding, right? So then so my probability is 1/2, right? So I have 50% of the time I make the right choice. So if I map it to this, then I'm good because I map the other one to here. If I do the other way around, then I'm bad. So 50% of the time I get an embedding. So it's 1/2 the coefficient. This guy like this guy has, because I can never embed non-edge, and this guy has, right, because I can embed the non-edge if I choose this vertex to be this, which is half of the time, and if I choose this vertex to be this, then I also am done. I'm also good. So this product is actually 1/2 times this fact plus 1/2 times this fact. And likewise, I can compute the other ones, right? I can compute empty times empty, non-edge times non-edge. I get this expression. And I can compute edge times edge. I get this expression. So non-edge times non-edge. I'm only good when I either, I'm only non-zero for this guy, because for the others, I cannot embed. So then, and here, the probability of this thing is 1. And here it's also 1, because it doesn't matter how I assign the vertices, I always get an embedding. All right, so this is the project in the algebra. And then there is a very nice observation regarding the project, right? So the limit functionals, they are actually multiplicative. remember the density is multiplicative. But if I define this product like I defined, since I defined the product like this, so here I have a joint. So if I take infinity, I can expand this as a product of two densities. And this implies a theorem that if you have a limit functional and you compute it in the elements of the flag algebra, the product commutes with the functional. So you get just the product of phi of f and phi of g. And this says something very nice, that moreover, if you compute the limit function, the unit of the algebra, you get, right, because the limit functional is given as a limit of densities, and the density of the type is always 1 inside whatever graph you consider, right? So this is always 1. Together, this means that limit functionals are actually algebra homomorphisms from the algebra to the real numbers. Okay, so it's a multiplicative function. It's a linear functional, and it maps the identity of the algebra to the identity of the reals, right? So it is a homomorphism of algebras, and it is also non-negative, right? So a limit functional is given in terms of densities, and densities are non-negative. So a limit functional is always a non-negative algebra homomorphism, and Rasborov proved the other way around. So he proved a theorem that says that the non-negative are functionals. Okay, and this is a very nice thing. It's related to this graph limits theorem of Lovász and Szegedy, that you have a sequence of graphs and they converge to an object, which is a kernel in that case. Here it's the same idea, but you are converging as a sequence. Your sequence of graphs is converging to this algebra homomorphism. And from this, Rasborov derives a way to use conic programming, right? So you can define a cone, which is the duo. If you look at a linear, it's in the and then you have like this duality between the functional and an element of the algebra. It's just right. And if you look at the set of homomorphisms and you multiply, you take all non-negative multiples, you get a cone in your algebra, and the dual cone is an important object in flag algebras. It's called the semantic cone. It's the duo of this cone. And actually, the bipolar theorem gives you that the duo of the semantic cone is this cone of limit functionals of positive homomorphisms. Then our problem becomes, you are optimizing, you want to find a limit functional, right? And you want to optimize the density of graphs, so phi of C, where phi is functional. You can rewrite it in terms of the semantic cone. You want to map it of C. Your has to be in the semantic cone, and you know, saying that when you compute that at a type, when you compute this guy at the empty type, because you want to do this for the empty type, right? You have an extremal graph theory problem. You get to 1. Okay, and then the nice thing is that you can get a dual problem of this problem. The dual problem is just lambda. So this is a conic problem with this infinite cone. And now you can minimize the subject to lambda times the empty type minus C, which is the objective function, below the cone. And actually, there is a strong duality between these two things. It's very easy to prove in this case. It's not a fancy proof at all. And then you can now try to find a good inner approximation of your cone. And this is what Rasborov shows how to do, right? So how do you find a good inner approximation of the semantic cone? Well, you can ask yourself, what are some flags what are some elements of your algebra such that any limit functional is non-negative for them? So what is an element cone has to be such that if you take any functional equal than 0, right? And there are some very simple ways to do that. So if you have, this is true, because a flag, so a limit functional is given in terms, right? And the of a flag is always non-negative. So this is, so a flag is always in the semantic cone. But other things are also in the semantic cone. Since a limit functional is multiplicative, any sum of is in the semantic cone. Okay, so if you have you can just expand them, and then you can take the square out, and then you get a non-negative number. So you get any sum of squares is in the semantic cone. And there is something also that Rasborov calls the downward, which it downcasts, it projects a flag. It projects the flag algebra of type sigma into the flag algebra of type empty by just forgetting the labels, basically, of the vertices, right? So you have some vertices that are labeled. If you just erase the labels, you get something out of it. You get this downward operator. You have to erase the labels and renormalize. You get something called the downward operator, and you can show that this downward semantic empty semantic cone of type empty, and that's actually why you need types, right? Because if you have these extra types that are not the empty type, you get from this downward operator, from applying this downward operator, you get a way of getting more elements of the semantic cone of empty type, okay, by using this downward operator. So you actually then use this SOS. So you make a flag that is a sum of squares by using positive semi-definite matrices. Here it is the same idea. I have only 2 minutes, but it's the end of it anyway. So if you just if you consider the set of all, and you take a positive, then you can write, just like when you write a positive an SOS polynomial, you can also write a flag by using this positive semi-definite matrix, and then you can project down this flag using the downward operator, and this allows you a way to find elements of the semantic cone of empty type. And then you can write a semi-definite programming problem, which looks very much like an SOS problem, which is like, you're minimizing lambda. Thing has to be squares of flags, so just some trivially non-negative object plus squares, and you want to find a positive matrix that is going to be the sum of squares. So that's how Rasborov and all these people that came after, they solved positive SDP to find bounds for extremal graph theory problems. And you see that the number of vertices of the graph disappeared in this business. Okay, so that's a very nice plus of this theory, that the number of vertices doesn't show up. So you are doing things for the limit, okay? And another thing that is quite interesting is that it's quite automatizable. So you can just generate a bunch of types, and you can just generate a bunch of flags, like everything by computer, and see what you get. So it's a very, like, if you don't get anything, you can try to go further. You can try to get more flags and more types, and then you can try to make a larger problem, and then you can see what you get. So many new results in extremal graph theory came from this approach of Rasborov, and actually in extremal combinatorics, because this works for other things other than graphs. It works for hypergraphs, for permutations, for many other things. Okay, so that's the end of my talk. Thank you very much. And if you have any questions,